Hello, I am Dr. Kyoung-Hee Kim, Professor of Architecture and Director of the Integrated Design Research Lab at UNC Charlotte. In this lecture, we will go over the third function in our sustainable envelope framework, regenerate. In the previous videos, we've discussed how building envelopes protect by shielding from outdoor environments and how they promote indoor environmental quality through thermal and luminous performance. But sustainability today calls for more than just protection or enhancement. We need to think in terms of regeneration. The book Regeneration, Ending the Climate Crisis in One Generation by Paul Hawken says, to reverse global warming, we need to reverse global degeneration. This is a call to action to design architecture that not only minimizes harm, but also contributes to regenerating resources and restoring natural systems. In the context of sustainable facades, regenerate means integrating renewable power potential and nature-based solutions, producing clean energy, capturing carbon, purifying air, or even generating natural habitat. It's about designing building enclosures that give back more than they take, creating value for both people and the planet. This slide outlines the three essential functions of a sustainable facade: protect, promote, and regenerate. Detailed explanations are available in the Sustainable Facade Introductory Lecture. In summary, first, building envelopes protect life safety and building structure by keeping out harsh weather and ensuring long-term durability. Next, they promote health and well-being by bringing in daylight, fresh air, and nature to enrich the indoor environment. Finally, building envelopes aim to regenerate by generating energy, restoring ecosystems, or filtering water. A successful facade integrates all three functions, contributing to resilient, regenerative built environment. To design solar energy producing facades, we first need to understand the nature of sunlight as an energy source. The sun's energy reaching on Earth consists of about 5% ultraviolet, 43% visible light, and 52% near-infrared. UV light, while a small fraction, can damage materials and isn't very useful for solar panels or illumination, so facades often include coatings or films to block UV. Visible light is a very useful part of the spectrum, not only because it allows us to see things and is the primary source of daylight for rooms, but also because it is what solar PV cells convert to electricity most efficiently. Infrared brings the heat literally. It's responsible for solar heat gain through windows and warming up interiors. Too much infrared can cause overheating, so efficient facades might use spectrally selective glass or shading elements to reduce energy transmission while still emitting visible light. By knowing that sunlight's energy is mostly in visible and infrared wavelengths, understanding the solar spectrum helps us design solar facade systems that harness solar powers while regulating the spectrum that causes harm or discomfort. Solar energy is abundant. Sunlight falling on Earth for 1 hour can cover more energy than the entire world consumes in a year. Now let's scale that down to a single building. On average, the solar intensity is around 550 kilo B2 per square foot per year. By contrast, a typical office building's energy use is around 55 kilo B2 per square foot per year, which is only 10% of available solar energy. Even allowing for inefficiencies, this means if we can capture a fraction of the solar energy hitting the facade on the order of 10% or so, we could theoretically supply all of the building's energy needs from its envelope. In practice, it's complex due to nighttime, weather, angles, etc. But the key point is that integrating PV panels into our building skins has enormous potential towards net zero or net positive buildings. This slide's takeaway: sunlight is plentiful. The challenge is harnessing it effectively. Sunlight is also bright enough to lit the space without relying on artificial lighting. Outside on a clear day, brightness can reach 100,000 to 110,000 lux. Lux is a unit of illuminance in direct sun. Even a blue sky without direct sun is around 20,000 lux, while indoors need on the order of 300 to 500 lux for typical tasks. Our facades receive abundant daylight, and we should design a facade that admits enough illumination while improving indoor comfort and reducing energy use for artificial lighting. This map displays the average solar source around the world. The colors indicate how much solar energy is reaching on each location. Red regions near the equator have much higher solar potential than blue areas farther north or south. For example, the sunniest areas, such as the Sahara Desert in Africa, deserts in the Middle East, and the Australia show the highest solar potential. In contrast, places at high latitudes like Northern Europe have much lower potential due to weaker sun and more cloud cover. This slide illustrates global distribution of photovoltaic installation. One thing to note is that the solar potential in the previous slide does not match the actual solar panel installed. For example, Africa receives 60% of the world's solar resources, but currently accounts for 1% of global solar production capacity. Another note is that solar energy capacity isn't spread evenly around the globe. Therefore, actual solar installation isn't just about solar potential, but also other supports such as political wills, financial capital, technology advancement, and infrastructure exist. This slide shows the ranking of the leading countries and regions by their installed solar energy capacity for 2023. China is by far the world leader in solar capacity, with over 600 gigawatts installed. EU member states collectively have around 250-270 gigawatts of solar capacity. Following that is the United States, which is third on this chart with roughly 140 gigawatts of solar capacity. Other major players include Japan, India, Australia, and South Korea. Many leading countries are making solar a mainstream energy source, and it hints at where the next leaps in solar adoption might come from if others follow these leaders' example. The chart shows the projection of the global accumulation of solar PV panel waste in 2050 under two scenarios. If panels last their full expected lifetime, cumulative waste could reach roughly 60 million metric tons by 2050. In a scenario where many panels fail or are replaced early, the waste could soar to about 78 million tons. It is estimated that there will be 4,500 gigawatts of installed panels by 2050. The graph highlights the importance of a circular economy and the reuse of retired panels. By 2050, an estimated 60-78 million tons of PV panel waste could equal the volume of thousands of buildings. We must design and implement PV panels to be easy to disassemble and reuse, as well as robust programs for repair, refurbishment, and recycling to extend panel lifetimes and avoid landfills. We need to turn a waste program into an opportunity. Solar technology is being woven into almost every aspect of our built environment today, with diverse contexts for PV integration, from infrastructure to urban interventions, architectural applications, and even everyday products. At the infrastructure or urban scale, we see large-scale implementations for greater impact. Even water bodies are being utilized through photovoltaics and solar canals, floating solar farms on reservoirs that generate power while reducing evaporation. China and India have some of the largest installations. Solar integration in urban environments includes solar noise barriers along highways and solar roads. There are also solar-powered public furnishings like the Fluid Cube in Hungary, a cube-shaped bench equipped with PV cells that power USB chargers and provide Wi-Fi in public spaces. In cities, we also see solar street lighting and lamps that charge by daylight and light by night. Solar technology is also applied in buildings and products. From the Powerhouse in Germany to solar-powered backpacks, these examples showcase the integration of solar energy into everyday life. Now let's focus on BIPV solar systems that have become part of the building envelope. BIPV consists of roof-integrated and facade-integrated systems. Facade integration can be used in glazing applications and opaque wall applications. From the top left of the diagram, glazing application, PV can be installed as sun-shading elements like louvers, brise-soleil, or canopies. Curtain wall systems can integrate PV modules either in the vision glazing zone or the spandrel zone. Vision glass areas can use see-through PV or place clear gaps between opaque cells for views outward and daylighting intrusion. Closed cavity facades and double skin facades incorporate multiple glazed layers and air cavity. For the closed cavity system, PV systems are suspended in the air cavity where the air cavity is sealed. A double skin facade can integrate PV cells on the exterior glazing layer or within the cavity. In these applications, the PV system serves as a shading device while generating power. From the bottom left, opaque wall applications include PV as a rain screen cladding or exterior panels on walls. Instead of metal or stone panels, the facade is clad in photovoltaic panels that protect the insulation behind it and produce power. Finally, roof integration on the right includes solar roof tiles or solar membranes. Roofs receive the most sunlight, so rooftop PV is effective and can articulate aesthetics such as dragon-scale shingle patterns, etc. Solar facades are multifunctional in that they provide the essential function of protect, such as weather protection, structural attachment, fire safety, etc., and promote of daylight, view out while also generating clean power, regenerate. BIPV facades should consider the aesthetics of a building, not be a band-aid afterthought. In essence, we can turn the entire facade into a solar power plant and potentially enhance architectural quality. This slide highlights a fundamental design principle balancing user experience of view out and energy harnessing. At the occupant's eye level, the facade transparent band allows daylight to come in, while it gives occupants an open view out, connecting them to the outdoors. The facade's upper and lower zones above and below the view band contains more photovoltaic panels. They are placed to produce solar power without blocking the view. Let's look at some real-world examples of regenerative solar facades. Federation of Korean Industries, FKI, tower in Seoul is an office tower that features a folded photovoltaic curtain wall. The facade is composed of horizontally folded glass panels, angled according to solar reaching angles. These folds are not just aesthetic, they help capture sunlight from different angles throughout the day. PV modules on those folded surfaces generate power, while the folds also create self-shading and conceal the slab inside. Next, Doctors Without Borders in Geneva incorporates a flat BIPV curtain wall. It integrates see-through photovoltaic panels in a flat plane as part of the curtain wall system. The look is modern and provides privacy from a distance. The entire facade is producing energy, illustrating that even a flat, conventional-looking curtain wall can generate solar power. Hanwha headquarters in Seoul reskinned their headquarters with modular BIPV facades. The facade has a distinctive geometric pattern of PV panels, each module of which was developed in balancing environmental performance and program inside. Each module is angled optimally for sun exposure, and together they form an artful mosaic over the building mass. Solar Skin Tower is a design concept project. It treats the entire high-rise facade as a solar skin. It employs vertical folded fins with integrated PV. The folds run vertically like pleated skirts to catch the morning and afternoon sun on their sides. This approach can be particularly effective for towers to increase the solar catching surface and create an iconic silhouette. Each of these examples illustrates a different language of solar facade: folded, flat, modular, tilted, woven. They also reside in different climates and contexts, proving that regenerative facades are globally applicable. Architects are using creativity to turn facades into renewable energy generators while still achieving aesthetic and functional goals. This slide exemplifies rooftop applications. Powerhouse Brattørkaia in Trondheim, Norway, is often cited as the world's northernmost energy-positive building. It achieves this largely with an integrated solar facade and roof. The building is shaped with a large sloping roof and facade surface facing south, clad entirely in PV panels. Even in Norway's less sunny climate, the sheer area of PV produces more energy annually than the building consumes. This project underlines that regenerative facades can enable buildings to power themselves and even feed surplus to the grid. Google headquarters in Mountain View incorporates a highly innovative solar roof known as the Dragon Scale Solar Skin. While it's primarily on the roof, its scalloped edges are visible on the facade. This system uses tens of thousands of small overlapping solar shingles that resemble fish or dragon scales. The dragon scale PV tiles have a textured, layered look that glitters at certain angles, turning the building's envelope into a dynamic tapestry of sunlight reflection and absorption. They generate 7 megawatt of renewable power on site. LAD headquarters, or veil facade in the lower middle image, is wrapped with a veiling screen of PV panels. The term veiling suggests a thin second skin, perhaps a perforated PV layer that hangs off the building. This PV veil likely filters sunlight, provides shade, and generates electricity. It creates a distinctive exterior appearance, almost like a lattice or scrim, showing that PV panels can form an artistic screen rather than a solid flat surface. The diversity of these examples highlights that solar facades are versatile and increasingly mainstream, especially for those who pursue RE100. Importantly, these projects address the aesthetics that they can be beautiful. This is a critical evolution. As architects and clients see successful examples, it builds confidence that regenerative solar facades can fulfill both engineering and artistic aspirations. This sun path diagram shows how solar orientation and panel tilt affect energy capture on a building facade. Aligning panels with the sun's path maximizes solar exposure. The optimal panel tilt is about equal to the local latitude for peak annual output when the PV application is facing south. Vertical facade panels aren't at this ideal angle. They catch more sunlight for low winter sun but collect less in summer. The takeaway: strategic orientation and tilt can boost a building's solar energy yield, improving performance and sustainability. Despite the progress and examples, there are still significant challenges to widespread BIPV adoption. This diagram illustrates the main challenge areas, which we can summarize in several broad categories. Let's start with 3 bubbles from the bottom. First, under technical efficiency and system design challenges, solar efficiency is continually improving, but installing PV in facades can be less efficient than on optimal tilt roofs due to suboptimal angles or partial shading. There needs design standards and regulations to help with implementation. Early BIPV projects sometimes were deemed unattractive, reinforcing a myth that solar facades can't be beautiful. Next, economic and market cost is a big hurdle. BIPV facades often cost more upfront than the facade without solar systems. Therefore, there is a need for better financial incentives and government policies to improve the economic situation. Education and awareness is another hurdle. There are many knowledge gaps and a lack of experience in the design, installation, as well as operation and maintenance of BIPV systems. Therefore, there's a need for more professional training and university curricula on BIPV to reach a wide range of stakeholders. Increased public awareness through demonstration projects can improve acceptance. Having more high-profile demo buildings can dispel doubts and allow people to see and experience BIPV's benefits firsthand. Many building codes prescribe rooftop solar and did not anticipate solar panels as part of the facade. The lack of specific building codes on BIPV facade applications causes uncertainties in permitting, fire safety regulations, and performance standards. The lack of standard design tools or code guidelines means extra effort is required for each project to prove compliance. While such challenges remain, we need concerted effort in lowering such barriers, and we can expect these systems to become ever more common in the push toward regenerative built environments. This video was supported by UNC Charlotte in collaboration with the US-ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in advancing sustainable building practices.